Alright guys, here we go, jumping into 2.6. 2.6 is a little lengthy, so we're breaking this one up into two parts. So a lot of this is all based on rational functions like these guys. So the rational functions, remember rational just means it's a fraction, you have x on bottom. So if you looked at page 213, you can see sort of a lot of the key features of the parent function that we're looking at right here. So I already drew that in so that we could see it. We've already talked about these before, and I know you guys have done these before, but we're finally get to go a little beyond what you've covered in Algebra 2, and so we're going to stretch that a little bit in this lesson and go a little deeper. So one of the things that we look at first in this is how do we use our knowledge of transformations to graph stuff like this, right? Or even more complicated like this. We've done things with a calculator, but we haven't really done these with transformations because of the way they're written right now. Like this doesn't really fit the transformation model. And so that's kind of what we're doing here in these first couple, is using some tools to put it into a way so that you could actually use transformation rules instead of a graphing calculator. So consider your parent function. Think of some of the main points that I plotted on here. So if you just think of numbers, if I would have plugged numbers in for x, I probably did the main 5. It'll look like this. So if you were to plug in those main 5 numbers, obviously 0 doesn't go in, but I plugged in a couple numbers to the left of 0 to create this curve, and a couple numbers to the right of 0 to create this curve that you see right here. We already know the vertical asymptotes through 0, and the horizontal is also through 0. So that's our parent function that we want to keep in mind. So what if we did something like this, right? So what they want you to do is they want you to write it so that it looks like the parent function, while sort of isolating and identifying what transformations are taking place. So here's the first one that they had done for you. And I'm going to try to zoom in here a little bit because I think this may not be a little clear if you don't have the notes printed in front of you. So let me try to help you out a little bit. See if that's a little better for you. So anyway, so if you look at something like 3 over x minus 2, how do we write that with this idea in mind so that it represents the parent function? So basically all they did on that was they said, well, let's factor out a 3 to make it look like this. So they factored out the 3, and now we can see it's basically 1 over x, but we're shifting to the right 2 units. So we got the 3 out in front. So that must be a vertical stretch because it's not attached to x, it's outside of the parentheses. So we have the vertical stretch of 3. And remember, all that means is your vertical stretches, you just multiply those times your y coordinates. And then you have your x coordinates being shifted to the right 2. So when you write it as 3 times a function of x minus 2, right, now I can see the 2 transformations taking place on this parent function. Right, I got the vertical stretch of 3, and I have the right shift, the horizontal shift to the right 2. So this is where you could then take this graph and apply those values to it. The shifting right and left, up and down is pretty easy, but when it comes to multiplying, when you get your stretches and your shrinks, those really help to actually identify real points and multiply. Right, and so if I actually identified some real points onto this, like if I had plugged in these numbers, and again I can't plug in 0, but if I plugged in -2, 1 over -2 is -1/2. 1 over -1 is -1, 1 over 1, and 1 over 2. So if I were to take those points, right, and here's where this gets a little more of an exact process. If I were to multiply all of my y coordinates by 3, and if I was to add 2 to all of my x's, that would create the new set of points that I would have for the new graph. Okay, and so that's kind of the approach they want us to take for this. So not the graphing calculator, they want us to actually use transformation rules with real points. What about something more complicated like this? So this is where your fun with long division comes into play. And so that's what we're doing down here. So this long division process, and this is why we reviewed this, really everything up till this point in the chapter has been review of Algebra 2. This is kind of where the new stuff kicks in taking what we've already learned. So when we look at something like this, we're going to use long division in order to create a scenario like this. So this is the idea, is by using long division. So we got the 2x plus 1 divided by x plus 2. So here's what this looks like. So they went through our long division process. They got 2 went in evenly. They had the remainder of -3. So remember how we write the remainder is we always write the remainder over the divisor, right? So we write it as either you could say plus. So you could put a plus sign right here and put your negative right there. Or you can just keep it as a minus like they did. Either way, however you see that more clear. Either way you do see it, understand, just like the one that we did first, this is a -3, right? And so if we factor that out, it looks like this. So our function of 1 over x is first of all being multiplied by -3. Then we have the horizontal shift right here. And then we get the vertical shift right here, right? So through that long division process, it helps us identify the 3 transformations taking place. And then I could do, apply those to the real numbers that we have here. Okay, and so we'll be practicing these in a minute, but I showed you right here basically how I did that. I just took one of the points on the graph. I took 1, 1, and I applied those 3 transformations to it to get a new point on the graph. Okay, and so we multiplied the, and remember I am using the whole shy 15 process here because we do have 3 things. This one affects the x's, and that's the only one that affects this graph horizontally. So it really doesn't matter when you do him in this case. However, these 2 both affect the graph vertically, and so their order does matter on that. So we do know that the S for stretch or shrink comes first. So we would multiply the y coordinate by -3. At the same time, I subtracted 2 from my x, and it gave me this point right here. Then last, we would do the vertical shift, which is to go up 2. So I added 2 to the y coordinate, and this would be the new point that we would see on the graph, right? And we would have to apply that to multiple points in order to get an accurate graph. So that's what we're going to be doing. Let me just mention, we've been talking about using limits to identify end behavior. So that's something else I want to just keep throwing out there. So when we see something like this, right, we're saying that, and this applies to the first graph, the one that we did up here. In fact, let me do this so you can see it. As far as the end behavior of the right side, remember the limit of the function as x approaches positive infinity, that just means the right side of the graph. What is the right side of the graph approaching? So you can see as I move to the right, my graph is getting closer and closer and closer to 0. It's doing the same thing to the left, closer to 0. So that's why as x approaches positive or negative infinity, my graph is approaching 0. And in this case, that applied to the parent function. It would still apply to the new graph as well. It's going to have the same end behavior because even though this thing is being shifted over, the horizontal asymptote is still 0, and it's still going to be approaching 0 even if you shift that whole thing to the right. However, I want you to see this part because we also have the end behavior here and here. So as we approach 2 from the right, that's the plus sign. And as we approach 2 from the left, that's the minus sign. What is our graph approaching? So remember, this whole thing got shifted over 2 units. Let me just sketch it out. In fact, I have it on the next page. Let me just jump over there because it's already drawn for us. So here was this first graph that we did, right? Everything got shifted to the right 2. We multiplied the y coordinates. So that's what I was doing right here. So here was 1 point on the graph. It went to the right 2, and I multiplied the y coordinate by 3. So here's what the new graph would look like. So we already talked about the end behavior as the graph approaches infinity, as x approaches infinity. But what about the end behavior in these locations where it approaches the vertical asymptote? So we said the limit of the function as x approaches 2 from the right, so that's this guy, right? He's approaching, here's positive 2. As we approach it from the right, what is our graph approaching? Well, it's going up and up and up and up. So our graph is approaching positive infinity. How about the limit of our function as x approaches 2 from the left? So that's this guy. So as x approaches 2 from the left, now we're headed towards negative infinity. So when this graph splits like this one did, we basically now have 4 end behaviors to describe. Limits are a great way of doing that though. So, and then here was the other one that we graphed. And again, you could go through, if you want to take a look at these guys, real similar idea that we just talked about. Let's try one. Let's try one on our own here. So we're going to jump down to this guy, and I already made space for this on the next page if you have these printed out. So let me jump over to that. So I already kind of set this one up for us. And then we're going to graph it. We're doing all kinds of fun stuff with this one. So guys, first things first, we already know some of the ideas about the asymptotes and things like that. Remember, if I set the denominator equal to 0, I know that -1 is my vertical asymptote. And if I did this coefficient divided by this coefficient, I know that y equals 2 is my horizontal asymptote. Although I think we're going to get a better idea of where that's coming from after we do the long division, right? So let me just go ahead and write that stuff real quick. So horizontal, we said x equals -1. Sorry, that was the vertical. Horizontal is going to be y equals 2. And so I had given us rules for that, but again, I think it's going to be helpful to be able to identify that as we set it up after long division. So we would say, what would I multiply times x to get 2x? I'm going to take that 2 and multiply it back in, so it becomes 2x plus 2. We subtract. -1 minus 2 becomes -3. So there's our remainder. So I'm going to say plus -3 out of my divisor, which is x plus 1. So this one's fairly similar to the last problem that we did, but that's okay. But because now I can more clearly see what the function is doing here. I can see that vertical shift of 2. I can see the horizontal shift at -1. I can also see my reflection because it's negative. We got a lot going on in this one. We also have the vertical stretch of 3. So let's see if we can sort of lay all that out a little bit better here, piece by piece. So I'm going to write, first of all, just my answer from long division. I always like my vertical shift at the end. So let's put that in terms of f of x, and as far as like our f of x represents the parent function, right? So what's being done to it? It's being multiplied by -3. We also have our horizontal shift of x plus 1. And then we got our vertical shift at the end. So this just helps us identify what transformations are taking place here. So when you do the reflection, we could do this as a separate idea, or you can sort of roll it into one move, where when you multiply your y-coordinate, you just multiply it by -3 instead of +3, and then doing the reflection, we're doing it as one move. And so I'm gonna do it that way. So anyway, this is why, and this is kind of one of the things I wanted to show you. When we talked about last chapter, I think it was last chapter, or maybe earlier this chapter, where the horizontal asymptote came from dividing this by this, you can see how that takes place here, right? Remember, typically your horizontal asymptote runs through 0. Well, if everything is being shifted up 2, that would include the horizontal asymptote. So instead of being at 0, this causes it to shift up 2, and now my horizontal asymptote is y equals 2. Okay, and so we can, that long division process helps us separate out the vertical shift, and that also helps us identify the horizontal asymptote. I kind of wish this had come up earlier in the chapter, but it is what it is. So if we were to apply that to some real numbers so that we could graph it, again, here I laid out the sort of the parent function values. So let's apply a couple things here. Remember that he affects the y, he affects the x, he affects the y. So as far as Chi 15 and the way that's laid out, the order on that matters if you're attacking the same values, the same letter. But in this case, like, he's the only thing that affects us horizontally, so I can do him at any time. These guys, I need to be careful on the order because these both affect us vertically. So that has to come first. So I'm going to do these two things first. So I'm going to multiply my y's by -3, subtract 1 from my x's. So that becomes those. Multiply these guys by -3. So he still is a no-go. All right, so that takes care of both of those. Both of those. Now I have to add 2 to my y coordinates to finish it off. So I'm just bringing over the x's, add 2 to my y's. He was supposed to be negative, wasn't he? All right, so let's take a look at, sorry, it's a little bumpy. So I took those points and I threw them onto the graph. One thing I always like to do too before I even try to sketch is keep in mind where your asymptotes are. So at y equals 2, I have an asymptote. And at -1, we got the vertical. Those are going to help us draw a good sketch. So we'll do something like that. So now I can really clearly see where my curves are supposed to go through the points that I plotted. So I'm just going to line up right up into those dotted lines and right through the points that I plotted. And we get some pretty accurate graphs that way. So really want us doing that within our homework, making sure that we're applying transformations and really only using the calculator maybe as a way to check an answer. But we want us doing all this process by hand today. As far as the domain goes, I always like to do the domain at the end after I've seen the graph. But now I can see that it's everything to the right of -1 as well as everything to the left of -1. So we can go from -infinity up to -1 and from -1 to infinity. So there's our domain. As far as the end behavior goes, keep in mind what we're looking at here. So as far as these guys go, we are approaching 2, right? So as I go to the right, I'm approaching the dotted line of 2, and as I go to the left, I'm approaching the dotted line of 2. So for these are both approaching 2, my horizontal asymptote. As far as approaching the vertical asymptote, similar to the other one that we saw, this one is approaching positive infinity from the left side. This one approaches negative infinity from the right side. So let's see. As we approach -1 from the left, we were approaching positive infinity. But as we approach -1 from the right, we are approaching negative infinity. There we go. So I just went back one page. This is kind of where we left off on this page before we started doing that last example. So something they're asking us to do on this one is just to find some key information, the asymptotes and the intercepts. So that's going to get worked out here. Let's just remind you guys of a couple things here when it comes to doing this. Intercepts, first of all, always associate with the word zeros. So if I want the x-intercept, I plug in a 0 for y, and I solve for x. If I want the y-intercept, I plug in a 0 for x, and whatever's left is my y-intercept. So by plugging in the zeros, we always get the intercepts. As far as the asymptotes go, we always know that sort of by setting the denominator equal to 0, we can find out our vertical asymptotes. So we can see by that at -2 and +2 are the vertical asymptotes. So one of the rules that we've talked about with horizontal asymptotes is when the top exponent is bigger than the bottom exponent, then there is no horizontal asymptote. However, here's one of the new things we get to learn. When the top exponent is one value bigger than the bottom, so this is x to the third, this is x to the second, when it is one value bigger, we actually have something called a slant asymptote that we'll see on the next page. How do we identify the equation of the slant asymptote? So when you do long division, the value that comes out right here is actually the equation of a line. So if I just have x, so think of the line y equals x and how we would draw that, right? It starts at 0, 0 and it goes up 1 over 1. So this acts as our slant asymptote. So let's take a look at all that on the next page here. And this is kind of our last idea, and we'll be trying this on our own. I wanted you to see this though. This was at the bottom of this guy, the one that we just did a few minutes ago. At the bottom of that page, here is just a reminder of the rules that we've talked about. So vertical asymptote we get by setting the denominator equal to 0. The horizontal asymptote rules that we've talked about before. So when the top exponent is smaller than the bottom exponent, it's automatically at 0. When these guys are equal, we divide the coefficients. And if its top is greater, then there is none. However, here's the new one. Slant asymptote when n minus m is 1. In other words, when n is one value bigger than m, we get the slant asymptote. So here is the graph that we were just seeing. So here's what we knew going into it. We found the only intercept by plugging in the zeros. The only intercept shown was at 0, 0. So that was the only intercept on the graph. We found the two vertical asymptotes by setting the denominator equal to 0. We found the horizontal asymptote, the slant asymptote with our long division process. So here is the slant asymptote for y equals x. So within those lines, we're drawing these curves within those lines. So how do we know exactly where to draw those curves? Let's just start from the left and work our way over here. So on the left side, we either know that the curve fits in this spot here or fits in this spot here, right? It's either above the slant asymptote or it's got to be below it. It can't cross over the vertical asymptote, so I'm either drawing the curve into that spot or into this spot. So how do we know where it goes? Well, remember the only asymptote that we found was at 0, 0. So if there's no asymptote here, I can't draw a graph here. Sorry, intercept. If there's no intercept here, I can't draw the graph here. So then therefore the graph must be here. The same reasoning is true on this side of the graph. Again, I know there is no intercept here, So I know the curve cannot be drawn in this spot right here. Therefore, it must be drawn in this spot between those asymptotes. So what about the middle? So we do know that we have the intercept at 0, 0. And yes, there are certain asymptotes that you can cross. So that does happen. The asymptotes still guide the end behavior of the graph, right? So this curve is still going to be approaching that line the farther you go to the left. And this curve is still approaching the slant asymptote the farther you go to the right. So it's still a guiding line, but there still can be a point where you touch or cross a slant asymptote and potentially even a horizontal asymptote as well. That can happen too. But anyway, as far as drawing this curve, so a couple ways we could look at this. I'll give you the sure approach here in just a second. But as you look at, say, this portion of the graph, right? You see how these guys are like opposite of each other, right? They fit that normal look of the graphs that we've been doing so far. Same thing is happening on this right here, right? You're getting these opposite curves from each other within those locations. They don't always have to be opposite though. So how do we test to be sure? Well, you could always plug in a number. So if I plugged in -1 in for x, I'm going to get a positive value. So I know that that side of the graph is above the x-axis. Remember, there's no more intercepts, so I can't cross it. So this portion would be above the x-axis. If I plugged in +1 in for x, I would get a negative number, which tells me in this area I'm below the x-axis, and that's what would help me draw the curves in, hugging up next to my vertical asymptotes. Let's try a couple. These can be tough. These are definitely new for us, so we're going to do those two problems and finish this off on the next page. So I already got it all laid out for you if you printed these. So here we go. So as far as the vertical asymptotes go, if I set this equal to 0, what are we going to get? Right, I'm going to get positive and -1. We're going to sketch as we go here. So I have my vertical asymptotes here at positive and -1. Horizontal asymptote, so let's look at the rules. Top exponent is bigger than the bottom exponent, so there is no horizontal asymptote. Since the top exponent is one value bigger than the bottom, we do know that there's a slant asymptote, and to find it, you're always going to use long division. So if I did x to the third try not to go too far with that. Maybe I'll move that over. I'm going to move it down here. So if I did x to the third divided by x squared minus 1. So going through our long division process, what would you multiply times that to get that? It would be x. X times that gives me x to the third minus x. Remember, typically we fill in the zeros here in order to get everything lined up with other terms. So we could have laid this out as plus 0x squared plus 0x plus 0 in order to get all of the terms accounted for. So that way, when you have something like minus x, you actually have a term to line it up under. As I subtract, those cancel. 0 minus 0, that minus that becomes x. And because that is now smaller than this, I know I'm just going to be left with a remainder. So what I see here is the equation of our slant asymptote. So this goes through y equals x. So remember, that would start at 0. It's going to go up 1 over 1. try to get this in a straight line here for you. Use this guy. Alright, so here is our slant asymptote. I always encourage you guys to do dotted lines for asymptotes. It helps separate out what's the actual graph from things like asymptotes, because asymptotes aren't really part of the graph. They're just guiding lines. They're boundary lines for where the graph goes. It's not actually lines on the graph, right? So it's always kind of good to have those. As far as, so we just identified this as y equals x. So let's look at intercepts. So if I set the whole thing equal to 0, I can get the x-intercept. So if this is 0, well, if I multiply this over, it's still going to be 0 equals x to the third, which tells me 0, 0 is an intercept. If I plug in a 0 for x, I get 0 over 0 minus 1, which is still 0. So again, that's going to be my only intercept, is right there at 0, 0. So that matters. That tells us a lot, because now as I look at the 3 sections of the graph, by the way, graphs are always divided up by vertical asymptotes. So if there's 2 vertical asymptotes, I'm going to have 3 sections of the graph. One here, something in here, and something over here. Okay, so as I look at the left side of the graph into this section, would I draw my curve right there, or would we draw it right there, right? And I can tell based on this, if this is the only x-intercept, then I cannot draw my graph right there, because otherwise I'd be creating another x-intercept. So therefore the only place to draw this is right there, and it should always hug up right up into those dotted lines that your boundary lines are. We can use the same reasoning for the right side of this. Again, I can't draw it here because I don't have another x-intercept. So instead of it being here, it must be up inside of these dotted lines. So I know that goes here. As far as the middle portion, how are we going to draw this? So you can get a couple different looks in the middle, so that's why it always helps to maybe plug in some real values to help draw the curves on this. So we could use the idea of limits to do this. If you started thinking about plugging numbers into this, the closer you will get to -1 from the right, so for example, if you started plugging in, say, -0.5, -0.9, -0.99, -0.999. So as you're plugging those numbers in, you would find that the y values get bigger and bigger and bigger and bigger, which is what tells you that as you approach -1 from the right, your graph should be approaching positive infinity. So I know that I would get a curve that goes this way. However, you can also keep in mind that really realistically, if I plug in any value right here, it's going to come out to be a positive number. And because of that, I know that the graph on this side of my intercept is all positive. And so it's going to have to go this direction in order to fit inside of the asymptotes that I've drawn. And that's why they're so important to have. So if you were to just test any number like -0.5, plug it in for x, you're going to get a positive number, which tells you over here my graph should be doing this. What about this region? Because potentially could our graph do something like this, where it sort of comes up into this region? Maybe, not likely, but let's say it's possible. With a slant asymptote, that's a little trickier to run into. With a horizontal, potentially we could do that. So it's still worth testing. So what I would do is, the idea of limits is awesome, and we spend more time on that later, but for purposes like this, I would just test a value. So if I plug in, say 0.5, I'm going to get a negative number, which tells me I'm not going up this way. It's got to be heading down that way. Okay, and so that's how we're going to get the graph. And so if you were to actually graph this in your calculator, again, you're going to see the 3 solid curves, you would not see the dotted lines. Those are just there as guides to help us draw the graph. So let's try one more with a little more going on in it to give you another example, and we're going to end on this. So again, a quick rundown of the rules. Vertical asymptote, set the denominator equal to 0. Only one vertical asymptote on this one. So at -2. So remember, it's the vertical asymptotes that separate out the sections of the graph. So this one's only going to have 2 sections. So I'm going to get some curve over here, and I'm going to get another curve over here. Only 2 curves for this one. Horizontal asymptote, we know there's none because the top exponent's bigger. Slant asymptote, because this exponent is 1 bigger than this, we're going to do long division to find the equation of our slant asymptote. So we're going to do x plus 2 into x squared minus 6x plus 5. So some quick long division, we would be multiplying by x times that gives me x squared plus 2x. We're going to subtract. So -6x minus 2x is -8x. Bring down our 5. Let's go through the process one more time. What would you multiply times x in order to get -8x? We would say -8. Distribute back through. And now when I subtract, I get 21 as my remainder, which you don't really have to write for this, but that's okay. Okay, so not the remainder, just this is the equation of our slant asymptote. So y equals x minus 8 is the equation of the slant asymptote. So this one would start at -8. On the y, it's y-intercept, and then it's going to go up 1 over 1 from there. And by the looks of this, I didn't make this graph big enough, so you know what we'll do. I'm going to make a quick adjustment. We're going to count by 2s. That'll make this work better. So I'm going to count by 2s on both axes. So this is my vertical at -2. There we go. So here I am at -2, 4, 6, 8. So I'm at -8 as my y-intercept, and I'm going to go up 1 over 1. So up 1 over 1 from there. Let's go up 2 over 2. So I definitely should have made this graph a little bigger, but that's okay. We're going to make it work. It's our last example. Let me see. I would be at... Go for a little accuracy here. So here is our slant asymptote. All right. So the intercepts, remember, those are going to help determine where the curves go. So as far as the x-intercept goes, if I set this whole thing equal to 0, well, as I multiply this over times 0, it goes away, and I simply have 0 equals x squared minus 6x plus 5. Let's just do that here. One way to look at this, and I try to avoid saying this rule in case there's any exception to it, but one way you could describe finding your x-intercepts is by setting the numerator equal to 0, right? Because if I plug in a 0 for y right here, well, as soon as I multiply this over, it's still 0. So all I'm left with is the numerator equaling 0. So that's really what we're doing to find x-intercepts. But anyway, we would solve that by factoring. Let's see, x minus 1, x minus 5. So we would get x equals 1 and 5. As our 2 x-intercepts. So that's good. That will help us draw our curves. And I got to remember I'm counting by 2s here. So at 1, 0, and at, let's see, 2, 4, 5, 0. I have intercepts, so that's definitely going to help us with this curve. As far as y-intercepts go, let's see what we got. As far as the y-intercepts, if I plugged in 0 for x's, all I'm going to be left with is 5 over 2, right, or 2.5. So let's say 2.5, 0 is going to be my y-intercept. So 2.5, remember I'm counting by 2's, is going to be like right there. So just by finding the intercepts, I can already draw half of my graph, right? So on this side of the vertical asymptote, I already can tell by just the intercepts where to draw this graph. So I know it's going to look something like this. Guys, remember, it will approach the dotted lines. So I know this is ugly, but when you draw the two end results, it needs to go toward the dotted line. It should not go like a U shape like this, and then it comes like up, right? It needs to be getting closer to the dotted line the closer you get to it. So it needs to like really hug up next to it. As far as this side of the graph, if we kind of use the same logic that we've used before, remember there's only two places to draw it. I can either draw it here into those inside of those lines, or I can draw it here inside of those lines. Well, as we've already talked about, I don't have any more intercepts, right? So I cannot draw it in this location. So my other curve must do something like this. And you could, of course, plug in a number or two to actually get some accuracy for that curve on where it would actually, like, what points it would literally pass through. But we don't have to do that in order to get the decent sketch that we have now. We're finding the main information that you're going to be asked for. So that is it for this one.